Okay, so welcome back everyone for Sam's final lecture.
Welcome everyone to the last lecture of my series of talks. So it will be about another somewhat different aspect of rigidity of manifold homeomorphism groups. So in the previous three lectures, we talked about one-dimensional diffeomorphism groups. Now we'd like to talk about higher dimensional ones. So of course, I really would like to hope to talk about diffeomorphism groups, but my knowledge is not enough. So today I will just restrict to the study of homeomorphism groups of higher dimensional manifolds. So this is the name of the talk is first order rigidity. This is joint work with Thomas Cabrera and Javier de la Nuez Gonzalez, who is at TIAS. So this starts with the with the theme of reconstructing spaces from groups. I'll just use a big blackboard. So reconstruction of spaces from groups. So the theme is that, as I briefly mentioned in the first talk, okay, so whatever mathematical structure you consider, there exists a group, which is the set of all the self-maps preserving the structure. So this is a well-defined map, but how much can you reconstruct X from purely algebraic information on automorphism of X? So that is our theme. So one may refer to Klein's propaganda on Erlangen program that symmetry and invariance are the two most important aspects of geometry. So in our setting, so our interest lies in compact manifolds. Of course, we'd like to talk about non-compact manifolds as well if possible, but for now, I'll just restrict our attention to compact manifolds, compact connected manifolds, and its connection to its automorphism group, namely homeomorphism group. And so I'd like to emphasize that we do not assume anything further than compact and connectedness, like no triangulability, no PL structure or smooth structure, any diffeomorphic structure, just compact, connected, locally Euclidean space. That's all. Then how much can you recover M from homeomorphism of M? So without reasonable assumption, that can never be achieved. Like, for example, compactness. So non-example or non-compact example is something that you can just think of right away, or we already used it. So homeomorphism group of real line is homeomorphic to homeomorphism group of compact interval, say orientation preserving. Or well, you can revert it both sides too. So they are obviously homeomorphic because open interval and closed interval, the extended endpoints will go to the extended endpoints anyway. So there is a natural isomorphism between them, and there are many slightly non-obvious, non-trivial examples. So I'll just mention the result without proof that even the sphere can be decomposed into two parts, such that homeomorphism groups are isomorphic. Or not homeomorphic, and you can even put some other conditions there, like transitive, and so forth. Transitive, locally connected, and homogeneous. But on the other hand, so there is a very fruitful and interesting direction of research proving that group isomorphism, so abstract group isomorphism, implies the isomorphism of two structures. So in the area of topology and geometry, for example, there is something that I already mentioned in my first talk. So if you consider manifolds, right? So there's topological manifolds and homeomorphism group. So homeomorphism group of, say, compact connected manifolds. So two compact connected manifolds, homeomorphism groups are isomorphic if and only if. So this is compact connected. The manifolds are homeomorphic. Okay, I'll just not write n parts. So to be complete, I should say homeo of m is isomorphic to homeo of n, then m is homeomorphic to n. So this is the result that I mentioned by Anderson in 1960s. And also Whittaker. Well, actually, I should mention Whittaker, not Anderson, sorry. Anderson is about simplicity of such a group, so slightly different. And then there are many other interesting results in this regard. So I also mentioned C0 case. So this is automorphism and structure. So CP and C infinity, these are the Takens-Filipkevitz theorem. And also building on the work of Axteby, Newland on good measures on manifolds and matter and Thurston. So building on these results, Banyaga established many other results in this direction. For example, simple ectomorphism group, or volume preserving group, or smooth diffeomorphism group, or contactomorphism group, and many others, several others. So if the symplectomorphism groups are isomorphic, then manifolds are symplectomorphic, volume preserving, homeomorphism groups are isomorphic, then the two manifolds are with equipped measures are connected by some measure conjugating map, and contactomorphism as well. Okay. But then, well, so you have a certain direction of research and conjecture, and after those conjectures are proved, you might wonder that maybe we have too much information so that these things are kind of trivially following. Like you're looking at continuous groups, topological groups with uncountably many elements. So there are uncountably many informations about relations and so forth. And then the conclusion is always that there is a homeomorphism or isomorphism between two structures, and even the original group isomorphism is obtained by conjugating this thing. So maybe there is too much information. So the question that I'd like to raise today is there a finitistic or property of homeo of M that captures N? Certain finitistic property or feature, but that is an ambiguous term. So I'd like to make a definition of this finitistic property in terms of model theory, first order logic. So the theme is that maybe we have just too much information. Just you're dealing with continuous groups. Maybe the isomorphism is too much information. It's not the right way of looking at those groups, because in that case, that is automatically becoming continuous isomorphism, and you extract the isomorphism between the structures. So what about some finitistic property? Yeah.
So we take a theorem.
Yeah.
So you want isomorphism as topological groups? Or
No. This abstractive group. That's a very good point. Right. It's abstractive group, but it becomes, after all, continuous group isomorphism because, after all, this is nothing more than obtained. This is just obtained by conjugation of homeomorphism. But the assumption is just group isomorphism, and Whittaker's approach is you just basically consider point stabilizer and send it by this given abstract isomorphism. Then it is just some group in the target, but point stabilizer has many nice group theoretic properties so that it becomes actually point stabilizer. So that is the heart of the proof. Right, so today so the aspect, the finitistic aspect that I'd like to focus on today is the first order feature. Okay. Or first order rigidity. So probably many of you have stronger background in model theory than I do because I almost had 0, but I just tried to use model theory to look at certain topological problems, but I really didn't have much before. So let me just briefly go over basics of first order logics, just at least have the definitions. So in the first order logic, we talk about language. So language consists of, so actually, depending on the authors and books and Wikipedia, there are many different terms for the same thing, but I'll just introduce the term signature. Signatures are non-logical terms. So these are like symbols. So basically, language is just a juxtaposition of many symbols. That's all. So, but in the interpretation of language, there are symbols for functions, there are functions for constants, there are functions for relations. There will be. So example to keep in mind is the language of groups. In the language of groups, signature have group composition and inverses and identity, and that's it. And then there are logical symbols and variables. Variables, it is x1, x2, and so forth. So countably many variables. Okay. So in this case, in the groups, you can also have x1, x2, but you can forgive me using G1, G2, G3 as variables because they are groups. But there are some countably many fixed variables. And then there are logical symbols, of course, to the logics. So you have equality and, well, and, or, negation, and implies. Of course, like you don't really have to have everything, but I'll just put everything. So you have these logical symbols. And then language is basically juxtaposition of these symbols, quantifiers, and quantifiers. Juxtaposition of these symbols. But some of the juxtapositions do not make sense. Some of them make sense. So I'll just not give a concrete definition, but a formula is juxtaposition or valid juxtaposition that is valid. Okay. So something that can be interpreted as mathematical statement or mathematical sentence. Okay. So that is a language. So for instance, in the language of groups, you can consider, say, for all A and for all B, A, B commute, right? Something like this. course, strictly speaking, this commutator is not in our set of symbols, but this should mean, well, we should be able to see what this means. So this is the abbreviation of ABA inverse B inverse. And I even omitted these composition symbols, but you can forgive me for that. So this is an example of formula. Or there exists some C such that for all A, for all B, CAB equals 1. Something like this. And you can even allow that for all A, AC, A, B equals 1. That is also a formula. Although this is not a complete mathematical sentence as is, because we don't know what B and CR is, but this is just valid sentence. Then you can quantify B before or not. It's just called formula. But what is not allowed, there are many things that are not allowed. For example, we don't want to put something like this. This just simply doesn't make sense. Okay? Or just like, yeah. Many other things like inverse of A or something like that. So something that can be interpreted as mathematical statement or piece of mathematical statement is called the formula. And the reason why I mentioned this is sentence is a quantifier-free formula. Okay. And this is really something that can be regarded as mathematical statement or theorem or false statement. And lastly, a structure or L structure. So L structure is really something that is the object of study in mathematics. So L structure consists of something, so L structure, say X, consists of its universe, which is a set, where you're gonna talk about these mathematical sentences or statements using these symbols, and interpretation. So each signatures should make sense here. For instance, you can talk about group structure. So what is a group structure? Well, so it is not the definition of a group, but if you're given with a group, right? So let's say some structure, say X. So there's a definition. I'm not making an axiomatic definition of a group. I'm just trying to explain the group structure when you're handed with a group. So group is given, then you can talk about this group structure. That is group, and composition is the group composition, inverse is the group inverse, and equality is the group inverse, and so forth. So everything makes sense here. Right? So that is group structure. Then you have, when you're given the sentence is either true or false in this structure, right? Because when you're given a quantifier-free formula, then that should be, by design, it should be either true or false. So again, there's a distinction between semantics and syntactics. So this is purely semantic thing. I'm not talking about axiomatic definition of group or undecidability or unprovability of statements here. I'm just talking about purely meaningfully that G is given, which we've been talking about for the whole week or for our whole life. And then there are mathematical sentences which gotta be true or false, right? So we collect all the true sentences. So I emphasize that this really has nothing to do with probability or unprobability or incompleteness. We just collect all the true sentences in the structure. The structure. X is a structure. It's called theory of X. Okay, theory of X is just collection of all the true sentences. Yes.
So in this group structure, are we also assigning a meaning to all these variables?
No. So, right, so variables will be used either quantified or sometimes it can be used like you plug something there. But variables, these symbols will be, so very strictly speaking, the symbol should be always x1, x2, x3, one of them, right? Strictly speaking, you are not even allowed to use GIs because you're gonna now compare theories of many structures of the same language. And says you'll see that like we say theory of X, we say X is elementarily equivalent to Y if and only if theory of X is precisely the same as Y, right? So I should say interpretation of signatures are the same. So each signature will have a meaning, right? There's one symbol will be the identity of group. Composition symbol will be composition. But the others are just used as they are. And when we say X and Y are elementary equivalent, if the theory of X and theory of Y are precisely the same as sets. So to be precisely the same. Yeah, quantifiers, yeah, everything. Interpretation of signatures and group structure, right? So theory true sentences. So sentence is just a meaningful formula, quantifier free formula. Quantifier free, sorry. I'm sorry. Yeah, this is my last day, so I'm losing. No unquantified formula. No unquantified. So everything is to be quantified, right? Because like if you have certain unquantified variable, this is not a complete mathematical sentence. But the first one is complete mathematical sentence. Right? So sentence means no unquantified formula. Every variable needs to be quantified. And then theories are exactly the same. You cannot express like, yeah, go ahead. So 3 is not in the symbol, right? But we'll get to that. But 3 is not precise. But 3 is not in the list of symbol. But for that specific example, right? Actually, 3 will be represented by another symbol, successor symbol. So SSS 0 plus 0 will be SS0 plus SS0 and so forth. These things are very strict. So for example, like Fermat's last theorem, you're not even allowed to write it as A to the N to the B to the N is C to the N. It should be X1 to the X2 plus X1 to the something plus X2 to the something should be X3 to the something. You're only allowed to use this set of variables so that you can compare the theories. Right? If you start, but in practice, we use like A's and G's and H's, but strictly speaking, you are only given this innumerable set of variables. So does it make sense? For example, like in the group structure, language of group, and if you consider the Heisenberg group, then the theory should contain that, for instance, for any ABC should be 0. Or there exists some B, non-trivial, such that, so, well, I can put such that, but such that is not also in the set of symbol, but we should allow that it just is something for human beings. So for all A, for all B commutes with A. So there is a non-trivial center and so forth. So these are theory of Heisenberg group. And of course, the abelian criterion is not in the theory. It's not in the theory of Heisenberg group. Right? Because there are matrices which are not commuting. Yes. Yep. So right. So So group structure. So these are signatures and variables and logical symbols, and that's it. That's it. Yeah. So in practice, we are just trying to list all the possible true group theoretic statements, sentences, that's all. So what are the possible group theoretic sentences that hold in the given group? So it seems like that we are very, like, our hands seem to be bound. There are not many freedom to do real mathematics, because all you can do is just group symbols, and that's it. And in fact, so it is, I'll just mention that Tarski's question, I mean, which is probably all of you already know, resolved by Stella Myasnikov-Kalankovich. That theory of F2 is actually, so F2 is equivalent, elementary equivalent. So we say elementarily equivalent. F2 is same as F3, and actually all the hyperbolic surface group too, called elementarily free groups. So at first glance, what is the most amazing is it took like 7 decades for the human being to resolve this question. So they are, so any true statements in these symbols in F2 and F3 and surface groups are the same. So sometimes, like, yes, right. So there are some unexpected elementary equivalencies. But today I'd like to, so right, so one last definition is that, so we'd like to study the opposite phenomenon. So let's say C is a certain class of structures, say L structures. So L is some fixed language. Okay. And then a structure in X is said to be first order rigid. So to be more precise, in C, if for all Y in C, if X is elementary equivalent to Y, then actually X equals Y. So this is the rigidity that I'd like to talk about. So, like, you can capture, at least in this class, you can capture everything about X by looking at this first order theory only. So, and then studying first order rigidity has been also interesting direction of research. So like Stella Myasnikov-Kalankovich result as well, and also many other groups. So many other groups, for example, linear groups. So, right. So higher rank lattices. Lattices are first order rigid in the class of finitely generated groups. So this is due to Avni, Lubutsky, Mary in 19. And some abelian groups, linear groups, and some rings I don't really know specific examples, but rings and some rings and function fields. So in the class of rings and function fields, people found first order rigid objects. But again, I'm just my interest is from topology, and I wanted to understand group theoretic properties of these homeomorphism groups and diffeomorphism groups. And like basically, I wanted to solve some of the questions that I originally have. Like for example, the conjecture that I mentioned, that is there a finite general group which is not C infinity smoothable, but CK smoothable for each K and so forth. So I wanted to use logics for such kind of questions. And the thing that I'd like to talk about is the manifold homeomorphism group and their first order rigidity. So the theorem that I'd like to prove is that, let's say theorem A. So if M and N are compact, connected, manifold, a priori with possibly different dimensions, even, but if homeomorphism groups are elementarily equivalent, then M is homeomorphic to M. Okay, so this is the thing that I'd like to talk about. So these homeomorphism groups are first order rigid. So two homeomorphism groups are elementary equivalent up to isomorphism, of course, up to isomorphism. So two homeomorphism groups are elementary equivalent if and only if they are isomorphic. And by Whittaker's theorem, you conclude that M is homeomorphic. And although our approach is just proving this arrow more directly. So this generalizes Whittaker. And also, this is a consequence of, well, the isomorphism implies homeomorphism is also a consequence of Rubin's theorem that I mentioned on the first day. And actually, the theorem that we are proving is something slightly stronger. So for all compact, connected, manifold, M, there is a sentence, Pm, such that, so Pm in language of groups, a purely group theoretic single sentence, such that Pm belongs to the theory of homeo of N, where N is for N compact connected, if and only if M and N are homeomorphic. So this is the actual theorem that I'd like to prove. Am I writing too low? Right. So for each compact connected manifold M, like for example, circle, there is a sentence, purely group theoretic sentence, like I am circle, such that Pm belongs to theory of homeo N, if and only if they are homeomorphic. But of course, we construct such a sentence by like several, like 50 pages of paper, so you cannot really write it. So it's just bootstrapping again and again and again. So it will be very, very long. It's just like the same case for the Gödel's I'm unprovable sentence. So people have written computer programs to write down the exact sentence, I'm not provable, but that is easily like several hundred lines, more than several hundred lines. So today I'd like to talk about the key idea of the proof. And before moving on, I'll just talk about a variation of the theorem. So you can also prove a measure preserving version of it. So let me give a more complete proof, complete theorem. So we consider class of pairs of Mg, where M is compact connected manifold, and G is something not too small inside homeomorphism group. We collect all such things. But for today's talk, you can just assume that G is the full homeomorphism group. But actually, the proof works for anything that is in between homeo 0 and homeo. And there's also M volume. It is collection of Mg such that M is compact connected manifold. And for some mu good measure, which I will explain, G is mu preserving group. And G is an identity component of mu preserving group. So M and mu look the same in my handwriting. So 0 mu means the identity component of the right-hand side. There is something isotopic to the identity through measure preserving homeomorphism group. But it is, so what is good measure? Good measure means something that is desirable for compact connected manifolds. So non-atomic, there are no atoms, fully supported, and boundary measure 0. So that's all. So that's the definition. Oh, and probability measure. So non-atomic, fully supported, boundary 0 probability measure. So this is some reasonable condition to study measures. And it is a non-trivial, highly non-trivial theorem of Fathy in 1980 that actually this identity component coincide with measure preserving, and that happens to be isotopic to the identity. So if something is measure preserving and isotopic to the identity, then you can find isotopy, which preserves measure in each time. So we consider these two classes of pairs, manifold and groups. But again, as I said, for today's talk, you can just simply assume that M is full homeomorphism group in the first case, and M is G is full measure preserving homeomorphism group of M. Of course, there are many good measures, but also it is a theorem of von Neumann and Oxtoby-Ulam that you consider two good measures, and they are nothing more than just conjugate by some homeomorphism. So group isomorphism doesn't depend on mu if you consider left-hand side, right-hand side. Okay. So then what we can say is that so actually theorem C is that so for all Mg inside this class M or volume, so I'll put the optional subscript in parentheses. There exists a sentence phi Mg depending on the group. Optionally, if it is volume preserving, then you put a different sentence such that this thing is in the theory of group, theory of homeo of N, or such that for all another pair, NH, in this M volume, this thing is in the theory of H, if and only if M is an homeomorphic to N. So you don't really have to have all the homeomorphism groups, but identity to the isotopic to the identity is enough for existential statement. So that's the point that I'd like to make. So you can, so even if G is very small, so only isotopic identity, that's enough to distinguish the manifolds. And also there is a version for volume preserving ones. You just delete all the parentheses, then there's this different theorem. So how do we prove such a thing? So let me give you the key idea, please. Or just brief summary of the proof. So it is due to a theorem due to Chigger and Kister, or actually a lemma in their paper. So in 1970, they published a paper proving something now people take for granted. So Chigger, Kister in 1970 is that the class of all compact connected manifolds are countable. So compact connected manifold up to homeomorphism is countable. Okay. And this is a almost trivial consequence of the following lemma, although they didn't state this as a lemma in their paper, it is implicit in their argument, is the following. So suppose you have a manifold M, n-dimensional manifold is given. So it is, we may consider even an embedding into R2n plus 1. So this is given, same is compact connected. And suppose you have a colored cover. Colored cover. It's another. So in other words, consider HI, where I is 1 through some number. So 10 plus 1 is probably enough, but some collection of maps from n-dimensional ball of radius 2 to the R2n plus 1. So these are all hypotheses such that M is union of this radius 2 ball, but it is colored cover in the sense that it is same as one ball is actually enough. So there are some slack outside, which doesn't really need to cover it, but you still require that this slack is contained in M as well. So this is hypothesis. Okay.
Problem with just taking time cover by one person, then make it goes one person.
Oh, embedding, sorry. Embedding, sorry. Yeah, today I'm making too many mistakes. Embedding, sorry. Sorry. Okay. Then there is some number epsilon, which let's call it as some Chigger-Kister number, positive, such that for any other scenario of another manifold n that is epsilon closed from this parameterization, they are homeomorphic. So I'll just write it down because it's also important to have the precise statement. For all n-dimensional manifold in R2n plus 1, satisfying exactly the same condition. So such that some GI, G1, GM are mapping n-dimensional ball into 2n plus 1 such that n coincide with dimension 2, radius 2, but also radius 1. And such that, so this is also hypothesis, sum norm max I is less than epsilon, then satisfies M and N are homeomorphic. So this is the right-hand side blackboard is a bit mouthful, but you can see what should be written there, right? So you have a same condition on another manifold for different colored cover. And if that is very close from the original parameterization, then they are homeomorphic. So it is kind of intuitively clear, right? Suppose you have a, say, genus 2 surface embedded in R3, covered by many balls. And now you perturb each disk a little bit. Then most certainly it won't be a manifold. But if the perturbation happens to be a manifold, then it should be genus 2 surface. That's all. But the proof uses some deep theorem of Edwards Kirby in 1970, saying that like if you have any manifold, you can isotopically move two compact sets under certain hypotheses. So this is the thing that we'd like to exploit. And the whole point is this Chigurh-Kessler constant depends only on M and the parameterization. Because if epsilon depends on N, it just simply doesn't make sense. It's just will be a nonsense. So for a given M and HI, there is some constant depending on the parameterization, such that anything that comes nearer than epsilon neighborhood of the parameterization, and under the hypothesis that it is also manifold, they should be homeomorphic. I should say, yeah, and it's a manifold as well. So our game is use group theory to represent this lemma, that's all. So purely group theoretic language using variables, group compositions, and inverses, we express what is written here. Because most of these things written here as they are not in the language of groups, like what is number 2, what is N, what is radius.
This HI, these are functions, right?
Right, sure. So this is
So what I'm saying is that that statement has to be translated.
right. So this is function, right? So this is not a good choice of the names of the variables. So GIs are functions. Has nothing to do with groups, as apparently. Right, so what do we do? So let me give you some interpretation of the lemma. And for the remaining, I have plenty of time, but the remaining time, I'd like to say a few words why it is feasible that we can express it in terms of first order. Okay, so let's see. What do you want to do? So goal can be stated as follows. Right. So now, we want to build some sentence. Just forget about the volume for now. Just we want to build some sentence such that whenever some abstract manifold is given to us, we look at the homeomorphism group of N and check whether this sentence is true or not. And checking whether this sentence is true or not in the homeomorphism group of abstract manifold N should be somehow equivalent to this Chigurh-Kessler hypothesis. Is it really epsilon far from the given parameterization? But mg is given, so Chigurh-Kessler, so in the hypothesis, mg is given to us. So Chigurh-Kessler constant is given to us, like 1/billion maybe. So that is given to us. And exploiting those information, we want to build certain sentence. So what do we do? So abstract manifold N is given. Then we want to express the existence of the following functions. So we want to build certain functions from, or check whether there exists some functions from all to Euclidean spaces. And let me be consistent with the choice of the variables. We want to check whether there is a function from, sorry, just to be consistent with my note, fi and di from n to the manifold n. And of course, we want to check, first of all, dimension of m is n. And we want to check whether there is an embedding fi, mvi, such that union of two ball is union of one ball should be n. And we want to build Chigurh-Kister type parameterization by composition. So that is, we consider VI inverse. So we want VI inverse, and you collect it for the suitable domains, and we want this to behave like Chigurh-Kister embedding of manifold in the R to the L. So that is for all X in the VI image of Bn2 and Vj image of Bn2, we want this collection to be a parameterization. So we want the values to coincide. So what is it? So you take a VI inverse and Fi. We want it to be coincide. Okay, so we have a Chigurh-Kister parameterization. And finally, it is in the epsilon neighborhood of Chigurh-Kister, original Chigurh-Kister. So supremum I of Fi Vi inverse minus the thing that is given in the hypothesis for M, Hi, is Chigurh-Kister of MH. Actually, so the Chigurh-Kister M of Hi. So goal is express this thing. In group theory, language of groups. Okay, that's all, right? So again, M is given, M and HIs are given to us. M and H are given to us. So Chigurh-Kister constant is also given to us. Now the goal is express that for a given manifold. First of all, the dimension is n. There is some function Fi of this form, Vi of this form, such that Vi inverse Fi will be an injective map, and everything is of course continuous. So this hook arrow means embedding, the topological embedding, not just injective map. And such that the supremum difference, the supremum of the difference is at most Chigurh-Kister constant. Okay. So this is highly second order statement using analysis is very far from, seems very far from group theory. But if we can achieve that, if we can achieve, if there is a group theoretical sentence, this will be actually equivalent to group theoretical sentence of M. So this is not a group theoretical sentence. I should say this is a sentence in like everything, like topology and everything. But if we can express this sentence in terms of group theory, then we are done. And that's it. That's the whole story. So the trick that we use is starting from group theory, we try to increase the expressing power of the language. For example, if you know about the groups, then you can talk a little bit about the open sets and so forth. So you try to empower the language so that it can express more. But mathematically, like still it should be the same. So that is the something called interpretation. So let me introduce Rubin's interpretation of group theory in terms of for the interpretation of Boolean algebra by group theory. This Rubin's expressibility theorem. So let me first of all right, so there's also another story. So Rubin proved this powerful theorem that I introduced in the first lecture, that locally dense actions almost determine the space. And in that paper is written in almost purely in modern theoretic languages, so I had a hard time reading it. And then he wrote several other papers with very similar topics, or probably targeted for group theorists or topologists. So those things I was able to digest. After our work is done and announced in a conference, so someone approached us saying that in 1989, Rubin claimed the theorem, and it's written in 1989 paper. Somehow I missed it. So we almost had a heart attack, but looking at the paper, so he said, like, in the forthcoming paper, we're gonna prove this. So what he claimed is that Rubin's claim is that, so if V equals L, I'm not the right person to answer what this means, but like roughly speaking, if von Neumann universe of the sets coincide with Gödel's constructible universe, the hierarchy of sets that are defined by first order sentences, then homeo n for any manifold, homeo n would imply m equals n. So that is what is written, and he says it is in the forthcoming paper, he will write about it, but he never wrote about it or mentioned or gave any hint about it in the 20 years following the paper. And he passed away in 1910s. So we never know. But and also there is a math overflow question we found out later that what did Rubin actually prove? And then there was one answer saying that like he never wrote about it, so we never know. So nothing seems to be known about the idea that he had, or I have no clue. Yeah. And then after uploading our paper on the archive, someone wrote a response to that math overflow saying that there's an archive paper regarding the question, but it's not us. I just want to clarify. It seems like, yeah, but none of us like put that, but someone put a reply in that math overflow post. So anyway, so the point is like Rubin made some claim using this V equals L hypothesis. And I really would like to know what his idea was. I can only guess, like right while doing this work, but probably he must have some beautiful idea because he's which I wish I could learn anything about it. Okay. Right, so what is Rubin's expressibility theorem? Well, so let me give Rubin's theorem on locally moving groups. Again, this is a very, very useful theorem, but not very relevant for today's talk. But so let's see. So let's say G is a group acting on a Hausdorff space. And such that it is locally moving. So for all non-empty open set, the group, which is defined as anything that is supported in U. is non-trivial. So that's the definition of locally moving. Whatever small open set you consider, it's doing something there. So this is defined definition of being locally moving. Then if G X on X locally moving and H X locally moving on Hausdorff space, then there exists an isomorphism. And if they are isomorphic of regular open sets to regular open sets. So let me explain what that means. So here, so this is the theorem. Here, regular open set is collection of all open sets such that its interior of the closure is itself. So for example, if you have a disk and something is missing without interior, so this is not regular open. So the whole point of considering regular open set is that, so if U is regular open, V is regular open, and U is not contained in V, then there's another regular open set outside U, inside V. So exterior of U and V is non-empty regular open set. So this is the use, the reason why regular open set is very useful when you consider subtractions or this locally moving business. Right, so what is isomorphism? Isomorphism in this regular open set is a Boolean algebra. Meaning that you have the notion of, say, U plus V, which is simply interior of the closure of union and intersection and empty set and negation. So negation is defined to be exterior of U and everything. So this is Boolean algebra and satisfies all the hypotheses of the axioms of Boolean algebra. The Boolean algebra is a certain structure. It is also a structure in the precise sense that I mentioned. So it is there's a language of Boolean algebra which deals with plus, which is interior closure of union and so forth. And then you can talk about any true statements using in the Boolean algebra. And he proved that this Boolean algebra are isomorphic, regular open sets. And then it is a group equivariantly isomorphic. And this is basically the most important part in the proof of Rubin's theorem on locally dense sections. And then he somehow pinpoint each point from many regular open sets by second order ultra filter to prove the things that to construct homeomorphism in the hypothesis, stronger hypothesis, locally dense sections. So why do I mention that? Well, in the theorem can be restated as first of all, he proved very interesting theorem in the process of the proof. Actually, this is really more than 90% of the proof. So Rubin's expressibility theorem is basically the almost everything in the proof for Rubin's theorem of locally moving groups. And it states that it's kind of I can never remember, it's kind of long sentence, but just to be entertained, let's write it down. Right? So in the group, let's say define eta G of some group element F. as collection of all the group elements satisfying. So it's in my book, so you don't have to really write it down. Every H in G, not centralizing F, there exists some F1, F2 in the centralizer of F, such that H, F1, F2 is not trivial, but centralizes G. It is some long sentence, right? So it's, again, this is in my book. You can download it. So then what he proved, and then he defined, well, it is not his notation, but he considered the set, which is centralizer of this mysterious exponent 12 inside eta set. Okay, so these are some definitions, right? Some first order definitions. Then his theorem is that G is Hausdorff space locally moving, and F is an element of G. Then you can express anything supported in F, or in other words, and F and G is in G, and support of. So I have to regularize each support. Let me make this definition. Support E of G is interior of the closure of support of G. It is a regularization of support. And support E of G is inside the support E of F. If and only if G is in this size set. And also you can trivially prove that using this. Support of EF and support of G are empty if and only if size sets are disjoint, which is trivial consequence. Okay. So this is, so the above are definitions, and this is the theorem. And it's, so if you've been working with group actions for a long time, this is really amazing because, well, having disjoint support implies they commute. That's also first order sentence, but it's very hard to extract anything further than that, unless it is inside some Lie group or something. So having like, but so even if two homeomorphisms are not having disjoint support, they might commute. So this is not if and only if with like two elements commute. But amazingly, there is a first order sentence. Everything is first order. So there is first order sentence that determines whether or not their extended supports are disjoint or not. Okay. Yes. Sorry, no, because it's like right. What is topological intuition? Right. So he never mentioned like this set. So this is a summary of his like 3-page sentences. Like so, in the first page he defined like first version of this, and then using first version many times, second version and third version. So this is like summary of his several pages of the definitions and argument. So it's very hard, but what is key idea? Well, right. I don't think I can summarize it in short time. So this is the thing actually he proved. And if it is not contained, the starting point, I can just give you the starting point. Starting point is that if it is not contained, then there is a minus. In other words, there is a some open set inside the support of G, but in the exterior of support of F, right? And then you have some element here moving, and then you conjugate and so forth. But yeah, for now, I don't have a good summary of the argument, but yeah. And of course, everything depends on this locally moving hypothesis. So without it, this is never true. And his idea is something called interpretation. So I have just time to define what an interpretation is. So, which once you get used to this very useful notion. So let's say X is some class. Well, first of all, you have two languages, L and L star languages. You can imagine that L star is a much powerful language than L. For example, L is just, for example, natural number. So it's just arithmetic with plus only, for instance. And L star is arithmetic with multiplication as well. So you can imagine that. You can imagine that L star is much stronger language than L, although for the statement of the theorem, it doesn't matter. And it's certain class of pairs such that X is L structure and X star is L star structure. So you just collect many pairs of structures for L structure and L star structure. Then we say X star is interpretable in X uniformly in X. That means that actually, if you know everything about, if you have an oracle that tells you true or false for each sentence in X, then you can do that for X star. So then what is that? What does that mean? That means that interpretable if the following hold. So this is a model theorist's understanding of what it means by you know everything about X star if you know everything about X. So there exists surjection, first of all, certain surjection depending on X and X star. So, well, first of all, uniformly. So there exists a sentence, say phi of domain and phi of equivalent in the language of in L. So there are certain formula, phi domain and phi equivalent. And also for all, say phi star, or let's call it psi in L star, there exists correspond psi, say hat in L, such that the following hold. Okay. So there is certain correspondence from L star formula to L formula. Okay. So the oracle needs to tell us what this is as well in the understanding of the meaning of the interpretability. And there is also domain and equivalent formula such that, and also there is a surjection rho from a certain subset, certain bunch of elements in some tuples for each X, such that this satisfies, this is the solution to the domain formula. Surject onto X star. So I'm kind of confusing the structure X and its universe. Anyway, so here X means the set. And we collect X bar. Certain tuple, which satisfies the domain. And that should surject onto X star. So for some mysterious surjection. which is fiber defined by phi equivalent. Okay, so X bar is same as Y bar if and only if it's equivalent formula holds. So you can define like when they coincide. And so if psi, so right. So we have if something holds in X bar in the structure X, if and only if the holds psi of is surject image X bar holds in X. And that's it. That's it. Right. So you can, so everything in new structure corresponds to many things in tuples of X, but the fiber should be definable and the domain should be definable. And some formula, the value of, so something holds, so that is right. More precisely, these are certain things. So PA holds, so this is some mathematical formula, so you plug certain things for A bar in X for some tuples of elements in the original structure. Then this should be true if and only if is psi formula chosen in L star holds in X star for psi hat is both. And it is called uniform interpretation because these domains formula, equivalence formula are not dependent on the choice of X and X star. Whatever X and whatever X star you consider, it should be definable. So I ran out of time, so I'll just give the last theorem that I can prove. So the key lemma is that the structure. So there is a structure containing group, regular open sets, real number and all the analysis, points in the manifolds, and all the continuous maps from R to the K to the R to the L. So this is some powerful first order language, which can talk about groups, regular open sets, each real number and their functions, and points in the manifold, points in the boundary, and all the continuous functions are now considered as object in the domain. So let's call this as L of all. Then for all manifold in MG, manifold or vol, there is this structure, all structure of MG. So this is the structure where language can be interpreted. So you can talk about all the regular open set, real numbers, you can talk about continuous functions. So all is interpretable in the group theory in MG, which is a group. So that's basically everything. So once you do the interpretation, then you can apply Chigurh-Kister and you can interpret, because now Chigurh-Kister can be stated in a formula in all structure of MG. And now that is interpreted in the group theory, so you can check whether that is true or not there by checking certain first order sentence in G. So that is end of the story. Thank you.
Other questions, comments?
About mapping possibilities, closer to free groups or groups of polymorphisms.
So in the eyes of elementary equivalence, I don't know. I don't know. I don't think it is known. I mean, this proving like elementary equivalence or elementary inequivalence is usually very, very hard unless you can easily find. So like proving elementary equivalence, if they are true, inequivalence should be easier because you have only to find just one sentence. Right? One is here, but that is there. But proving equivalent is usually much, much harder.
A lot of this was started off by this cheaper history.
Yeah, right.
So where you have manifolds built in.
Yeah.
So, and that leads you to, in your last lemma, putting in essentially this continuous functions from R
Yeah.
points in and all of these as objects.
Yeah.
Okay. What if you relax that a little bit and just say something like homology manifolds, where there is a throwing away of structure, but still in something that's algebraically something that you can say. And
Okay.
you don't need to get into the more sophisticated part of the language, which is very highly second order. So just define objects to be things for which you have a local homology theory and you have it's hn of x minus x is c.
Okay.
So I mean, this seems to be a more general context in which
I
some of this might
see. I
actually-
see.
So of course, homeomorphism is not the right thing, but would have to be
I see.
structure preserving maps of homology maps.
I see.
Just
So-
some way to take out the Rn from the list. Yeah.
Right. What is the goal there? You want to show that two manifolds are homologous? Yep. Or like, yep. So,
I mean, it should be some sufficiently added up version. Here you're getting
right. Yeah. So that,
I don't know what the right isomorphism is that category is.
right. So yeah, that
It's just trying to algebraize the theory from the analysis.
yeah. So that is certainly interesting. So I didn't mention anything about Rubin's interpretation, although I planned. So Rubin's interpretation is that, right? So he interpreted Boolean algebra, group actions of Boolean algebra, purely in terms of group theory. So that is actually Rubin's expressibility theorem, because so in Boolean algebra, actually partial order determines everything. So once you have partial order, then partial order is expressed in terms, this is the interpretation map, psi goes to psi hat. So once you interpret partial order, then you can interpret everything about the Boolean algebra and group action. So in this case, and then although this seems like analysis, so it is kind of also some finitistic information in disguise. In other words, so what is continuous map from R to R? How do we encode continuous map R to R? Well, you have only to know the values at Q. Right? So this is subset of Q to the R. Right. So this is, in cardinality wise, this is 2 to the omega times omega. And so this is 2 to the omega. So you only need one real number to encode a continuous function. And one real number using Dedekind cut, you only need to know second order theory of arithmetic. So if you can talk about subsets of integer set, then you can talk about real number. So you can talk about continuous function. Oh, no, so I mean, but in this correspondence, if you go through this correspondence, one real number here encode a continuous function. And a real number is encoded in this way. In other words, the subset of n. So what is subset of n? Well, in manifold, you consider regular open set with countably many supports. And any subset having full connected component. is subset of n. So if you identify n, u with the integer set n, then this is some subset. So this is how you interpret a subset of integer set. And then you define what is plus, what is multiplication. Interpret those things. So you can talk about subset of n. So the point is like the continuous function is also naturally interpreted as a subset of some regular open set. So what would be a reasonable question there? Like isomorphism homeomorphism group or isomorph? Right. Yeah, I don't recall anything. So what would be questions like circle, for instance? Right. So if you consider quasi-symmetry group of the circle, and then what do you want to know about it, for instance? So first order theory of quasi-symmetry group. Of that, I have no idea. I mean, we really would like to know about the diffeomorphism group, for instance. So one thing that I didn't mention is that now it gives us a countable subgroup of homeomorphism group, which captures the homeomorphism type because it is Collem's theorem, but it is also easy to prove that this theory. So although the group is huge and uncountable, this is only countable collection of finite sentences, finite length sentences. So this should be realized by some countable subgroup. Whenever you see universal variable, you put just another element if you need, and so forth. Existential. So for all manifolds, there exists some GM, countable subgroup of homeo of M. So it is countable thing, but these things are never isomorphic unless the manifolds are homeomorphic. So that is one of the motivation that something that we would really want it to do was find finite general subgroup, but right, yeah. Right. So we would really like to do the finite general case, but currently, yeah, we don't have idea. So yeah, quasi-symmetric, that's interesting. And like, for instance, can you, for instance, distinguish quasi-symmetric group from smooth circle diffeomorphism group by first order theory? I think that's a legitimate question.
Okay, so let us thank Sam once more for the whole series of lectures.